Imagine a machine so small it fits in the palm of your hand, yet powerful enough to push the boundaries of what we believe reality allows. Not a thought experiment. Not science fiction. A real device. In late 2024, Google's quantum processor, Willow, completed a benchmark calculation in less than 5 minutes. According to Google's estimate, the same task would take one of today's fastest classical supercomputers an unimaginably long time, far longer than the age of the universe. This wasn't simply another performance improvement. It represented an entirely different way of processing information. That staggering comparison immediately raised a fascinating question. If a quantum processor can solve certain problems so dramatically faster than conventional computers, what is actually happening inside the chip? Most headlines focused on the speed, but the true story goes much deeper. The comparison wasn't meant to suggest that Willow is faster at every task. Instead, it demonstrated how quantum computers can outperform classical machines on very specific problems designed to highlight quantum behavior. Classical computers process information one step after another. Even when billions of calculations happen every second, they still follow a sequence. Quantum computers operate according to entirely different principles. Rather than relying only on bits that represent either 0 or 1, they use quantum bits, or qubits, which can exist in combinations of states until they are measured. This property, known as superposition, allows quantum systems to represent many possible configurations simultaneously. Even more remarkable is entanglement, a phenomenon that links qubits together so strongly that the state of one cannot be fully described without the others. As more qubits become entangled, the mathematical space describing the system grows exponentially. Once a quantum processor reaches well over 100 high-quality qubits, the number of possible quantum states becomes unimaginably large. It quickly exceeds numbers we encounter anywhere else in science. That doesn't mean the chip literally stores more physical objects than exist in the universe. Instead, it means the quantum state is described by an enormous mathematical space. This distinction is crucial, because it often leads to confusion. A classical computer physically stores information in transistors. A quantum computer doesn't physically contain every possible answer inside its hardware. Instead, its quantum state evolves according to the laws of quantum mechanics, allowing certain algorithms to explore possibilities in ways classical systems cannot efficiently reproduce. Even so, this behavior feels deeply counterintuitive. For decades, physicists have debated what quantum mechanics actually means beneath the mathematics. One famous interpretation is the many worlds interpretation, first proposed by Hugh Everett. According to this idea, every quantum event corresponds to multiple possible outcomes that continue in different branches of reality. Many worlds remains one interpretation among several. It has neither been proven nor disproven by experiment, and there is currently no scientific consensus that quantum computers literally perform calculations across parallel universes. Yet the idea continues to capture attention because it offers an intriguing way to visualize quantum behavior. Imagine facing a puzzle so enormous that solving it alone would take longer than the lifetime of the cosmos. Now imagine countless versions of yourself exploring different possibilities simultaneously before the correct answer finally emerges. While this is only an analogy, not a literal description, it helps illustrate why quantum algorithms can appear so astonishing compared to classical methods. What quantum computers actually rely on is interference. Quantum states combine in ways that strengthen the probability of correct solutions while suppressing incorrect ones. Instead of checking every answer individually, carefully designed quantum algorithms manipulate interference so that the right answers become more likely when the system is measured. Exactly why quantum mechanics works this way remains one of the deepest mysteries in physics. Some researchers view interference purely as a mathematical feature of quantum theory. Others find interpretations like many worlds conceptually appealing because they provide an intuitive picture of the underlying mathematics. At present, no experiment has demonstrated that quantum computers exchange information with parallel universes. Even without such extraordinary claims, Willow represents an important technological milestone. For years, one of quantum computing's greatest obstacles has been error correction. Qubits are extremely fragile. Tiny disturbances, from heat, electromagnetic fields, or microscopic vibrations, can disrupt their quantum state, causing valuable information to disappear through a process called decoherence. Traditionally, adding more qubits also introduced more opportunities for errors. Scaling quantum computers without losing reliability became one of the field's greatest engineering challenges. Google reported that Willow demonstrated continued progress in reducing logical error rates as more physical qubits were incorporated into its error correction system. That result suggests researchers are moving closer to building quantum processors that become more reliable as they grow larger, an essential requirement for practical quantum computing. If these advances continue, the impact could be enormous. Quantum computers may eventually help scientists design revolutionary medicines, discover advanced materials, simulate complex chemical reactions, optimize transportation networks, accelerate certain artificial intelligence techniques, and solve scientific problems that remain out of reach for classical machines. Yet every major technological leap brings new questions. Humanity learned to use fire long before understanding chemistry. We harnessed electricity before fully understanding electromagnetism. Nuclear energy arrived before society fully appreciated its consequences. Quantum computing may become another chapter in that long history of powerful discoveries preceding complete understanding. What makes quantum computers unique is that they embrace uncertainty instead of eliminating it. Their power emerges directly from superposition, entanglement, and interference, the same quantum phenomena that have puzzled physicists for over a century. Willow does not prove the existence of the multiverse. It does not open portals, communicate with parallel worlds, or demonstrate realities beyond our own. Those ideas remain speculative. What Willow does demonstrate is that quantum mechanics allows information to be processed in ways that differ profoundly from classical intuition. That alone is extraordinary. Every generation builds instruments that expand humanity's picture of reality. Telescopes revealed that Earth is not the center of the cosmos. Microscopes uncovered invisible worlds of living cells. Particle accelerators exposed the hidden building blocks of matter.